All right. Well, last time we were talking about transport. And in terms of recap, the questions we posed ourselves were, if we know the governing equations that describe behavior, what happens in terms of our ability to use this cheap and dirty formula that the arrival time is equal to the length traveled divided by the effective velocity. When is that true or not? We know that's true if Peclet number is bigger than about 10. And the question was also, is the concentration that you see downstream similar to the concentration that it starts off with upstream? We know that in some cases it's not going to be that case. So in the case where we have lateral spreading, we would expect that we had some dispersion and that by definition the peak concentrations would not be the same as it goes downstream because of this geometric spreading of the plume. But in a one-dimensional case, we might expect that it would do. We didn't talk about the equations that describe one-dimensional flow of a slug going downstream. We do have those equations here, and you can use them. It describes a time at which the plume arrives. It would arrive as a center of mass in the same way that we could look at the plume for the case of the downstream. Well, if this was time and this was concentration, we would think that the downstream arrival would look something like this. So we always think that in terms of the 50% concentration, that really it describes kind of a center of mass. We have enough present at this location as we do at this location. It's just merely being spread. Likewise, in the case where we have it going downstream as a spike, we would expect that this mass would be conserved. So that each of these cases, if you look at the area under these plumes, we'd expect that there would be the same area in 1D, if it's 1D flow. And so this peak does actually get shorter. I guess you can get the time at which the peak occurs here. So if the Peclet number is equal to 1, this becomes 1 squared. So 1 plus 1 is 2, square root 2 is 1.4 minus 1. So the arrival is at a relative pore volume of 0.4. And just to kind of do completeness, that equation, instead of me using equatio, is actually plotted here. So for Peclet number of 1, then this arrival of this peak is basically at 0.4 something, which is here, which we've just determined. And so although this peak is kind of shown here as being equal to a relative concentration of 1, it actually diminishes as it goes downrange. And so we see the same thing as with Peclet numbers as we did for a continuous source, and that is that the behavior for very large Peclet numbers would be just like a spike, and it would be honored. We know that these relative volumes under the plume for these different Peclet numbers should be the same, and so the reality is that this peak is reduced, and so that is intrinsic in those equations that we mentioned here, in that we're not going to use them, but in that you can calculate what the time of arrival of the peak concentration is. If you know that time of arrival, you can plug it into this expression here for whatever Peclet number you have. This gives you a value of E, and this goes into this magnitude here, which allows you to get these magnitudes that reduce as they go downrange. And so that's the case where we're still talking about what we will refer to as conservative transport, in that mass is conserved within the water. It merely spreads out as we go downrange. But now we'll talk about non-conservative transport, which is where mass in the water is not necessarily conserved. So that's what we'll talk about today. And we will look at these effects in terms of attenuation, means that maybe some of the mass gets sorbed onto the grains and is lost to the water phase, and that in doing that, then maybe the plume arrives down gradient more delayed than it would otherwise be. And so to do that, we need to talk about what these mechanisms are. And they're important mechanisms. Attenuation, of course, is what you might rely on if you want a plume just to take care of itself and to not do anything. And so, one of the strategies in dealing with groundwater remediation is to put in a stopgap, pump and treat in perpetuity, just hoping that the source of the plume attenuates over time and that you don't ultimately have to do very much with it. So that's what we're talking about today. We know that we were talking about this advection dispersion equation. It exactly describes exactly what our behavior is. This would be the profile for either a spike source or a continuous source, maybe dissolving in the subsurface, and how it looks as you go down gradient, with the front of the plume and the 50% concentration defining the center of mass, if you like, relative to that. And we'd like to be able to calculate these plumes for the cases where we have retardation and attenuation. It can occur for a bunch of reasons. It can be absorption of components onto the grains or into organic carbon, as we talked about maybe at the end of the class yesterday. And it could be a whole series of reactions that affect it. But regardless, the effect is the same, that we're not conserving mass. Not going to talk about that. That's from Fetter, absorption. Not going to talk about that. But we might expect that we could represent the behavior by some kind of formality in terms of a mechanism and representation. We've talked before that this represents mass in minus mass out. It's conservation. And this represents accumulation. And so what we could imagine is that we have some other terms on here that accommodate a change in concentration, which is the accumulation term, but change in concentration rather than just arriving in the control volume, it could change due to other things. Two species dissolved in water could react with each other and cause a third species, in which case the concentration would change, which would be a term like this. Or we could have sorption being representative of the same thing, and we could represent that sorption as a net loss to the accumulation. Instead of accumulating stuff, we're negatively accumulating, if you like. And we can define that typically in terms of a density of the bulk density of the aquifer, rho sub d, the proportion of the aquifer which is water-filled, which is the volumetric moisture content. So this is it's equal to the porosity if it's 100% saturated. And if it's less than 100% saturated, it would be the proportion, which is the volumetric moisture content. And this is the concentration of the solute, not in the water, but plastered onto the grains or into the organic carbon, which the water is flowing past. And so this value of dC star is defined as the amount that is sorbed per unit weight of solid, in the solid of the aquifer. And so we're going to assume that this is kind of can be represented by an equilibrium process. For instance, if you take a bucket of sand and you put in a solute that's dissolved in water into that sand, then you might expect that the concentration on the solid would change over time, and you like that time over which that would change here to be quite short, so small. And so we're looking at equilibrium behaviors when this is completed. And so if that's the case, then we can represent this by another process. And what we could do is that we'd like to write this term in a common language to this. So what we could do is we could multiply both top and bottom by the concentration in the water. And if we do that, then we can join terms like this, and these two terms on the cross diagonal. dc dt, of course, now is in this form. And if we do that, then we're able to, if we can define exactly what the change in concentration on the solid relative to the liquid is, then we can define exactly what the behavior is. So if we can define this term, which we will call a distribution coefficient, which is equal to dc star over dc. Concentration on the solid versus the concentration in the liquid. And so if we can define this as a parameter, then we can merely move this term to the left-hand side, which is what we're going to do, and combine it. That's our plan. So this at the bottom is exactly this. We can take this concentration with time. We can multiply top and bottom by dc dc, which is just 1. If we do that, then we can define exactly what the top left to bottom right diagonal term is. No, sorry. To determine exactly, to be able to exchange this term here for a value which is dc dt. And so what we would do is we would take a bucket. That bucket would have our aquifer in it. We would pour some fluid into it which has something dissolved in it. And I guess we would measure for that fluid, we could measure, to define exactly what it is, distribution coefficient. It is going to be, I guess, the concentration on the solid versus the concentration in the water. The water has some concentration in, and we know what that is. We leave it in contact for some time, and it gives you a concentration on the solid. Likewise, you double the concentration in the water. Maybe it doubles the concentration on the solid. And we draw a straight, maybe a straight line through there as a linear isotherm, which is what we have here. And we've defined our distribution coefficient merely by our definition as C star over C. So this is KD over 1. So this is exactly this. That's it. So if we can define, by doing a little experiment, how much is sorbed onto the solid, we can define our distribution coefficient. This distribution coefficient is this term here, this gradient term here. We're assuming that as we add this water, it'll take some finite time for it to sorb onto the solid, but we're looking at the value once it reaches equilibrium. So this is an equilibrium value here. I guess just like the capillary pressure saturation curves, it would start off, as you add the water, it would start off at this value, and then it would go up to here, and then it would go up to here, and up to here. This would be the equilibrium value, which we take, and therefore get that gradient. It might not necessarily be linear, it could be nonlinear, and so there are a bunch of isotherms that you might expect to find. Simplest is the linear isotherm. Nonlinear ones are Freundlich isotherms, which are just a power law, which depends on whether the exponent is less than or greater than 1 as to which way it slopes. And a common one that's used, for instance, in coal and organic carbon is a Langmuir isotherm, which says that this isn't with time, but this is with concentration. This one here was with time. So these are equilibrium concentrations. This is saying that as you increase the concentration in the liquid, you get up to a maximum value, And the typical interpretation is that at this stage you've saturated all the sorption sites on the surface of this material and it can't take any more. And no matter how much you increase this concentration of the liquid, the amount that gets sorbed onto the solid doesn't increase at all. And so we can define these isotherms in terms of this. So once we have that value, what we could do then is we can go back to our expression. We can do exactly what we said we'd do and take this as a concentration on the water per unit concentration on the water. That allows us to take this term and to move it to the left-hand side. And of course, the term on the diagonal here is really K sub D, what we've called it. And so bulk density, volumetric moisture content times Kd gets multiplied by the concentration gradient. We add it to both sides, so we end up adding it to this side. And so the expression that we have then becomes this expression here, written only in terms of concentrations in the liquid. We've thrown away the concentrations of this when we're ignoring reactions. And if we gather terms, we get a term called the retardation coefficient, often given the terminology uppercase R, which says how much it affects the rate at which fluid flows through the system. So if we replace this by R, what we could do is we end up with this term here, which is R. If this sorption effect is 0, then this is just 1, and it's the null effect that we've expected to see before. If it's finite, then it'll be greater than 1, and then maybe we have to worry about it. And what we can do is we can just divide both sides through by R. And of course, this is always positive. Density, distribution coefficient, and volumetric moisture content are all positive values, so it has to be greater than 0. So together this has to be 1 to infinity is the range, I guess. And perhaps we'll see some values which might be of the order of 30 as a maximum value. And of course, when we write the equation this way, it says something about what we expect for this behavior to be affected by, right? So the previous equation we tried solving was that the accumulation term was exactly this, it still is, and it had a dispersion coefficient and an advective velocity. So what we've done in this manipulation is we now have an effective dispersion coefficient and an effective advective velocity. And since they're divided through by a number which is 1 or greater, then each of these parameters is going to be reduced. And since we also know exactly what these individual parameters, how they affect the shape of the plume, we could probably guess exactly how it might affect our shape. So if our previous plume looked like this line here, we think that the center of mass around this front, the 50% mark, half C over C0 is 50%, occurs downstream a length which is equal to the advective velocity times time. Then the fact that we've retarded it, it's moving more slowly, so on a given time it will travel less far, the length it will travel will be, you'd expect, would be this amount here. The length would be this divided by a number equal to or greater than 1, and so that says exactly how that center of mass would shift. So we've retarded it, it's delayed in its, so it'll take longer to arrive downstream. But the other thing that we've done is that we've also reduced this parameter. And this parameter, as you remember, if it's equal to 0, then it's advection only, and it's an absolutely sharp front. And as dl gets larger, it progressively cants over the interface. So the other thing that you'd expect here is that not only has it moved this back to this location, but it's also made it more steep. It's so-called sharpened the front. and that's because the dispersion coefficient is less. And so we could use that to think about what it would affect to our plume. I suppose the other thing that we could do, since we're very clever now, is that we've also tried to solve this problem in terms of Peclet numbers, which are equal to a velocity times a length times a dispersion coefficient, and a Courant number, or pore volumes, which is it velocity times time over length? Yes, it is. So velocity times time is the length that it's traveled. You compare that to the length of the core, and of course that's one pore volume when it's equal to 1. These are advective velocities. And I suppose what we could do is that we now know that we're working with an effective advective velocity, which is divided through by this, and an effective dispersion coefficient is divided through this. So if we put in these effective values into this, we get V over R and dl over R. So no effect. So retardation has no effect on Peclet number whatsoever. But it will affect the value of the retardation coefficient because it affects this parameter here. So if we wanted to solve this equation using the methods we've talked about, we could use the equations for plug flow or for spike flow and solve it exactly, but just use the corrected Peclet numbers, and everything would be hunky-dory, and we'd get some behaviors that would do this to the transit in the aquifer, and I guess it would also have the same effect in the retardation RTT curve. Not retardation, is it? It's RT. What's an RTD curve stand for? Residence time distribution. Thank you. Yeah. losing my mind. So what would it look like? It would look like, I guess this would be the unretarded one. So this term here would be, this is time. So this time is equal to length over velocity, right? Yep, okay. And I suppose if we were looking to see what it would do, then the new one would look like pretty good, perhaps. So two features. One is it arrives earlier. Sorry. Is that right? Doesn't make sense, does it? That's exactly not where it is. It's going to be here, right? So now this length here, so if we write advective velocity as V over R, then we get an R in the numerator, and therefore the time it took to arrive would be longer, and the front would be sharper. So that's exactly what we would expect. Okay, so that's kind of so everything that we've done so far, we can apply using our advection dispersion equation. I suppose if we also wanted to do it for a two-dimensional problem, where we have a term which is d transverse over r d2c. I guess I should clean this up maybe. doesn't it do that? I don't know. In the y direction, so if we have a plume, downstream is the x, cross stream, if you write, is the y, and we have this thing that generates like this. So we could solve that equally well. It's just the effective dispersion coefficients should be the ones that are corrected by the retardation factor. And this might be a number 1 or larger. And so everything we can do is transportable. So we've moved from being conservative, pressing the wrong buttons here, not a political statement, transport. Meaning that the solute is not conserved. It disappears from the water. It's not conserved in the water. It disappears onto the solid matter that is static in the aquifer. Okay. All right. So let's go back to Borden. We talked about this experiment yesterday, Tuesday. So this experiment was run by digging a hole, putting some solute in it, a cocktail actually. We only talked about the chloride ion in it yesterday, on Tuesday, but also PCE and carbon tetrachloride were put in there, along with chlorine, sodium chloride, just salt. As it goes downstream, if you take a snapshot in time and look for the plume with your capillary tubes, you find that the conservative tracer, chloride, not sorbing onto the sand, has gone the furthest, and ones that are sorbed onto the sand or onto organic carbon that's in the aquifer travel different lengths of time downwind. So we could think of the retardation factor as being equal to a velocity of the conserved divided by the velocity of the non-conserved, right? The velocity of the conserved will be higher relative to this, and so this will be greater than 1. If we define those terms as velocity is equal to length over time, then this would be equal to the length of the conserved species divided by time, t, conserved, and the length traveled by the non-conservative species in the time non-conserved. And if we take our snapshot, did I just move this? No. How do I get back to red again? Oh, there we go. The snapshot in time is both at the same times, so it's 1. So this is just the ratio of the lengths traveled. So if we take the ratio of the lengths traveled, the length of the conservative after 647 days, essentially almost 2 years, is 57 meters. And for carbon tetrachloride, it is 23.5 meters. This is actually, what would that be? That would be 47, so that's about I think it's 2.5-ish, right? Something like that. Likewise this is for carbon tet. And these are what the plumes look like individually. For PCE, it looks like it would be 57 divided by 13. About 4, something of that order. So that's one way for us to be able to see what this retardation factor is. If we want to turn this retardation factor into a parameter that we can use elsewhere, then what we could do is we could use it to define the component behavior within our system. So we define the retardation by a distribution coefficient, so-called distribution coefficient, multiplied by bulk density of the aquifer and the volumetric moisture content. So we know the units of this have to be equal to nothing, because we're adding 1, which has no units to this, so this has to be dimensionless as well. And so we can see what the value of Kd that we might want to use would be. And so I think we do that right here. So here's what the aquifer density might be. 2,000 kilograms a cubic meter might not be a bad number. If we write that in terms of a volume, we know that a cubic meter is 1,000 liters. So we can write this as 2 kilograms of solid per liter of volume, which is the same as 2 grams per milliliter. If we take the retardation coefficient and we rearrange it in terms of the distribution coefficient, we merely subtract 1 from R, and then we divide both sides through by bulk density and volumetric moisture content to isolate it. We have this, and then we can look at what these values are. For carbon tetrachloride, it was 1, I guess it must have been 2.42 for R. And for PCE, it must have been 4.38 from those ratios of the two lengths. Subtract 1, multiply by whatever the volumetric moisture content. This is going to be equal to, if it's saturated, which it is, it's equal to the porosity. A value for porosity, not a bad one, might be 30%. And a value for bulk density in terms of kilograms per liter are 2. So this value here is that. And so if you do that, we end up with a value of the distribution coefficient, which is in kind of strange values, but it's a volume per unit mass. So I guess it's a volume of aquifer per unit mass of, it's basically a volume of aquifer per unit mass of solute is kind of what it's representing. And so we have a value here. This stuff down here we won't worry about, but we'll use that perhaps next time. Because what we'll find out is that we can define usefully the value of this Kd directly from a bunch of tables for organic solvents. We can use what's called the octanol partition coefficient. Partition coefficient. Don't know if I really want, I don't want to talk about it too much now. It basically says you can go to charts, tables that tell you how octanol partitions to carbon. And so if you know how much, which is the main sink for these components as they go down an aquifer. So if you know how much organic carbon you have in your aquifer, and you know how the octanol partition coefficient is for your particular species, carbon tet or PCE, you can estimate exactly what Kd is directly from a bunch of tables. And so we'll do that next time. But for now, all we need to know is that if we had an experiment like this, we could define the retardation coefficient just by the ratio of lengths that it's traveled downrange in a given period of time. If you take a single snapshot, we can use that to manipulate it if we have those data to be able to figure out what the distribution coefficients would be. And if we know what the distribution coefficients are, we could then predict this behavior. And of course, what we'd like to do is really predict this behavior if we don't have this behavior initially. And so the only way we can do that is if we're able to define exactly what the KDs are as a function of something else. And that's what we've just mentioned about the octanol, I guess they're octanol water partition coefficients. And we'll talk about that next time. So that's about it for retardation, delays in arrival, and attenuation, meaning that when it arrives, it might arrive, I guess, the point we didn't make, it might arrive at a concentration which is lower, right? Because it's being removed from the aqueous phase and plastered onto the solid. So it could be that this is reduced. So that's another consideration that we might want to be aware of. And I guess finally, the final point would be that we could also imagine that we have similar behavior occurring not just in porous media, which we've talked about so far, but also in fractured rock. And it could be because of sorption-like behavior, or actually sorption itself. So if we have this thought exercise of we take a fracture in rock, we have flow within that fracture carrying a plume downstream, and if it goes from upstream source to wherever the front is at some time t1, and we drew a picture of what that plume looked like along the fracture, it might look like this. And so it is that it has a sharp front, it's got a length which is given by the velocity, advective velocity of the front, and we could calculate exactly where that is relative to the 50% concentration. And so this is where there's no sorption onto the walls of this fracture. And indeed, that fracture's wall is impermeable. So none of the fluid goes into it. If we have a case now where we have a permeable wall rock, then even if there's no sorption onto that porous medium, what you could imagine is that within this wall rock, if you take this part here, sitting right next to the fracture, you might imagine that you have some grains here. And so as it travels down gradient, some of the stuff comes out of the fracture, goes in and has this tortuous mechanical dispersion path, perhaps comes back or perhaps spreads further into the porous medium. And so if the solute is being removed from the fracture and ends up in the porous medium, then you'd expect that, one, the concentration of the fracture might be reduced, but also it's effectively being retarded in the porous medium. And if you did a section along the length of the fracture, you might find that it looks like this. So it looks as if it is being retarded because this length now is shorter. It's actually not sharper, so that's kind of a key that you'd expect it to be, but it isn't. But this isn't because of sorption, this is merely due to mechanical mixing, and it looks like sorptive behavior. If you now allow the stuff that is diffused and dispersed into the porous media to actually be sorbed onto the solid, then now it is physically removed from the liquid, and so you've reduced the concentration in this, and you'd expect to further retard the advance of the plume, and perhaps also to maybe bring down this concentration here because the concentrations in here are being sorbed onto the solid. So we won't talk much about fractures other than to make the case that you can end up with behavior which looks like sorption but actually might not be, strictly speaking. But maybe you could attempt to replicate that behavior by using modified dispersion and advective velocities to be able to represent this behavior. And actually, if you think about it, there's not, I guess if you wanted to do it, you'd have to actually increase dr in this case, right? Because this front here is actually not sharper than this front, and that's what we'd expect if we have retardation going on. So that's about it. So, yeah. And some narrative to talk about that. So next time, what we'll talk about is how we can get the value of distribution coefficient from some tables that exist in the literature from some of our favorite organic chemicals. We can get it from these octanol water partition coefficients, and we can also get it from the solubility of those chemicals in water. So if you know what the maximum solubility is within water, either one of those terms will allow you to determine what their sorption capacities are in organic carbon. And if you know how much organic carbon you have in your aquifer, which isn't very much in Borden, the site that we just looked at, you could calculate exactly what the retardation and attenuation would be. And then we'll talk about a couple of other things. So that's all.